All right, here we are in Chapter 1, Section 4. We're talking about Calculus 1, and the topic of this section is exponential functions. And for the format of this video, I'm going to go through a homework assignment that I built using WebAssign and James Stewart's calculus book, Early Transcendentals 8th edition, and I'm also going to be trying to demonstrate how you can use your other resources in order to answer some of these questions and questions in general. And basically what I'm going to encourage you to do is to find the answers yourself, because there's not always somebody hanging around, a tutor or a professor, to sort of hold your hand to the answer. And if you've made it to Calc 1, chances are you're a pretty good learner on your own already, which is great, but I will be toggling over to the ebook in order to assist my own students in particular in finding the answers to some of these questions and encouraging you to do your own exploration. So let's get started looking at this material. And the first question, which is question number 2. Why does it say question number 2? Is there a number 1? There is. All right, so we want to use the law of exponents, and this is still, to an extent, review material. So some of this I'm going to move through fairly quickly. Some of these problems I'm not going to finish. Sometimes I will just show you what the properties or laws are that you need to be using in order to answer these or the rest of these on your own. But here in number 1, we want to use the law of exponents to write and simplify this expression. And don't forget that exponents mean to multiply something by itself that many times. That seems very basic, but sometimes we try to distribute an exponent when we're not allowed to. In this case, however, because what's contained in these parentheses, or I should say just in these parentheses, the expression inside those parentheses contains only multiplication. So under those circumstances, we are allowed to distribute our exponent. Generally, if I had a times b to the power of 6, I could write this as a to the 6 times b to the 6. And so we're going to do that here. I've got b to the 8th power, and we're multiplying that by 2 to the 6th power times b to the 6th power. And as a final step in this process, you'll take 2, raise it to the 6th power, which is 64. We tend to write our constant multiple or our scalar first, and then we'll attach that to b to the 8th times also b to the 6th. As another general property of exponents, don't forget that if you had m, let's not use m, let's use r to the m times r to the n, you can add the exponents together because that's a total of how many multiples of that value you have. So you would write this as r to the m plus n. Now if you actually know what m and n happen to be, then you'll do that arithmetic. So this problem, problem 1, part A, you would add the 8 and the 6 together and express your final answer. In part B, we have a quotient. I would tend to chop this up and look at just the numerator first and then rewrite it over the denominator. This denominator doesn't have to be modified at all, so let's have a look at the numerator. We'll take the 6 and raise it to the 4th power. We also have to take y to the 3rd and raise it to the 4th power. And then we'll put all of that over to y to the 3rd. This allows us to recall another property of exponents that says if we have x, for example, raised to the power of m, and then we're taking that quantity and raising it to the n, in this case we can or need to multiply the exponents together. It's like we have n groups of m multiples of x. So in the problem that we're working on, we can take the 3 and the 4 and multiply them together. 6 to the 4th power is whatever that is, and your y will be raised to the 12th power, and then we'll divide that by 2y to the 3rd. Whatever number it is that you have here, 6 to the 4th power, you'll evaluate that. You'll take that number and divide it by 2, and that result will sit in front of y to what power? Yet another property of exponents. If you have x to the m divided by x to the n, the n multiples on the bottom will literally subtract away from or cancel out from those m multiples of x on the top, and you will be left with x to the power of m minus n. Now if m minus n turns out to be a negative number, and I'll write up a quick example of that, then that would appear in the denominator. Or you could write it in the numerator with a negative exponent. Let's just do that real quick. What if we had x to the power of 3 over x to the power of 5? That would equal x to the negative 2nd power, which we could write as 1 over x to the positive 2nd power. So in the problem that we're working on, we've got y to the 12 over y to the 3. We'll do the subtraction and end up with y to the 9. So you've got your coefficient in front of y to the 9th power, and that'll be your final answer there. If my pen would work. I try to write boxes around my final answer, but sometimes the pen does not cooperate. So a little review of properties of exponents. Did we cover all of them here? We've got the product rule happening up here. We have the quotient rule generally happening right here, product, quotient, and the power rule for exponents is happening here. You might also, it might be beneficial to remind you that if you have a value or an expression, whatever it is that's being raised to the power of 0, the result of that is going to be 1. Anything to the power of 0 is equal to 1, except for 0. What else might I remind you of? This is actually a good reminder for you here that the negative in an exponent position tells us to take the reciprocal. So if we had x over y to the negative 2nd power, that would be equivalent to y over x to the positive 2nd power. So the only thing that I addressed there or applied was the negative part of the exponent. The negative took the reciprocal, then we could apply the remainder of the exponent. In that particular case, you would end up with y to the 2nd over x to the 2nd. We could dissect that further, but you've probably done that in an algebra class and don't need to see that again. Now, in problem number 2, we're asked to write an equation that defines the exponential function with base b greater than 0. Define the exponential function. Now, this is where I'd like to toggle over to the ebook, and we'll see if technology cooperates here. And pretty good. So I've logged into WebAssign, and I'm looking at a student view, and what that allows me to do is, if I can find it, top dead center pretty much, it says my ebooks. I'm going to click into there and borrow Stewart's calculus book. And it's loading, and I've got my table of contents here. I know that I'm in chapter 1, section 3, so let me click into chapter 1 and then scroll down into chapter 3, or chapter 1, section, oh, we're in section 4, sorry, I just finished making a section 3 video, and I'm going to click on, right next to where it says 1.4, I'm going to click on exponential functions, and that puts me into that part of the ebook. And there it is. In general, the exponential function is a function of the form f of x equals b to the x. So it was very easy for me to use my ebook in order to find the answer to that question. Now, can I get back to where I was? And the answer is no. All right, so we are back there we go. So we have our original instructions, and we toggled over to the ebook, and we found that, well, the base of b, the exponential function, is b to the x. There it is. Whew. Moving over to the ebook and coming back took way more work than I thought it was going to. What about the domain of this function? If b is a number greater than 0, which we were told that it is, right? You can see at the top of your screen, base b greater than 0. What's the domain of this function? Can I take a positive number and raise it to an exponent that's a positive value? Definitely. What about a negative value? For sure. We just talked about that property in the previous problem. What about raising a number to the power of 0? Absolutely. We just talked about that also. So it appears that there are no restrictions on the domain of the exponential function, in which case, using interval notation, you're going to express all real numbers. If b does not equal 1, what is the range of this function? Let's see if we can, more gracefully this time, pop over to the ebook. That was not graceful. There we go. And let's see if we can see anything about the range of the exponential function. Hey, here's an example where we have y being raised to the, or y equaling 2 to the second power. And we can see that this curve moves up into the first quadrant. As you move to the left, it's going down into the second quadrant, and it looks like it's just skimming along the x-axis there. So this is telling me that the range of this function, at least using a base of 2, the range appears to be going from 0 to positive infinity. Now those are the y values, the range values, going from 0 to positive infinity. Infinity always takes a parenthesis, but what about the 0? In this case, because the curve is never actually reaching the x-axis, the 0 is also going to have a parenthesis. Now that's just an example, right? We don't want to say, well, I saw one example and therefore no matter what my base is, as long as it's not 1, my exponential graph is going to have a range that goes from 0 to infinity. But if you look more closely at and you scroll a little bit farther through your book, we can see some different base values from left to right. We've got a half and a quarter, a base of 10, 4, 2, 1.5. All of these graphs are staying above the x-axis. Whether they're rising to the left or rising to the right, they all seem to have an asymptote, a horizontal asymptote that is the x-axis. You might note also that orange horizontal line is the graph of 1 to the power of x. The range for that function is different. That has a range where all of the y values are the same. They all have a y value of 1. So that's why the question that we were looking at, the question made this distinction where we wanted to talk about a b value that did not equal 1, because that has a very specific answer. The range of that is 1. But as long as it's not equal to 1, your range is still going from 0 to positive infinity. I have to enable my pen if I want to write anything. And I have to choose a pen. It's very demanding. So our range here is going from 0 to positive infinity. Sketch the general shape of the graph of the exponential function for each of the following cases. So if your b value is greater than 1, and you could toggle back over to the ebook, which I'm not going to do because it's not playing nice, that graph is, well, I'm not going to tell you. I'm going to leave it up to you to do that. You should go check out the shape of the exponential graph for a b value that's positive. And we have another question where b is equal to 1. That was the orange graph that I pointed out. And if your b value is between 0 and 1, so we're still working with non-negative bases, or b values, And there were, on that previous graph that we looked at from the ebook, it did have examples of graphs where the b value was fractional, or between 0 and 1. What about this question? Let me slide this over. This is question number 3, and it says, how is the number e defined? Well, you probably remember the number e. It's an irrational number, like pi. It's a decimal value that goes on forever and does not repeat, so it's irrational. It cannot be expressed as a fraction, and I'm going to be adventurous and try to make it over to my ebook again. It worked. So here I am still in chapter 1, section 4, and I've scrolled all the way to the end of this section, and it does not tell me anything about the value of e. E is a positive number. I should be able to use that as a b value, as a base for my exponential function. I should be able to take whatever e is and raise it to the power of x, and yet it's not appearing here. So I'm going to click on the right-hand side of the screen on this right-facing arrow over here. That takes me to the next portion of this section, and it's titled Applications of Exponential Functions. Applications is code for word problems. I might find a definition in here, but if I'm one of my own students, I go cruising through this section also and I still don't find it. So I figure, what the heck, let me turn to yet the next little subsection of the section, and lo and behold, it's titled the number e. So for my students, and for those of you who might not be my students, I'm going to leave it up to you to do a little bit of research, whether it's online or in your own ebook, and figure out the answer to this question. Why, when I come back, it keeps defaulting to that, I don't know, so I apologize. I'm going to scroll back down here. How is the number e defined? You're going to go into that section of the book and find out. What is the approximate value for e? Round your answer to 5 decimal places. You can look up the value of e. I would be willing to bet in whatever book you're using it gives a decimal approximation for e, and it's approximation because e is a non-terminating decimal. It goes on forever, so you couldn't answer with an exact value for e. So you're going to round it, in this case, to 5 decimal places. And what is the natural exponential function? What they're saying there is, what's the b value for the quote-unquote natural exponential function? And the word natural might remind you of natural log. And the natural log function is the inverse of the natural exponential function. So the fact that it's natural is telling me that we're working with the value e. And for the natural exponential function, your b value, your base, is going to be e. So I will let you type that in and frame it up so that it looks like an exponential function with a base of e. Oh look, here's the exact same image that we saw in the ebook. All we had to do was go through the homework some more, and we could have gotten some visual indicators for what the range of an exponential function is going to be, where our b value is not equal to 1, or in this case, there's the answer for the range when b does equal 1. And here they want us to make a rough sketch of the graph of the function y equals negative 3 to the negative x. It's a good thing in the previous section that we talked about transformations, and if you didn't watch the previous video, you can hop back over to the 1.3 video and review transformations. This one's a little bit different from problems we talked about in that section, because here the parent function is y equals b to the x. And we didn't look at exponential functions in the previous conversation about transformations. However, this, based on our conversation in 1.3, is f of x. So when we apply the current question, which is y equals negative 3 to the negative x, and we try to match it up with this format and apply some transformations, what's really happening? Well, the negative that's to the left of the number 3 this negative sign is outside of the application of the exponent. So I would say, I'm going to move back over to the right here and switch to a blue pen. I'm going to say that that's y equals negative, and then my function, f. Now, is anything happening inside the function? Can I just put an x in here, or do I need to put something else? The 3 you don't have to worry about. That's the lowercase b. So we're not going to be changing that. But the exponent, b to the x, if you look to the left again, you'll see in our original question it's 3 to the negative x, not positive x, or I should say, it doesn't just say x. So we do need to change this x right here into a negative x. And when you look at the question that we're working with, which is where I'm erasing right now, when you look at that question and you sort of compare it to this format over here to the right, and you ask yourself, well, what kind of transformations are going to happen? The thing that I've circled in green gives you a better idea. The negative that's outside the function is going to cause a vertical reflection because we are negating all of our y values. F of negative x is going to generate some y values for us, but before we use them, we'll apply this negative that's outside the function. So that's going to cause a reflection over the x-axis, a vertical reflection. Now, the negative that we're seeing on the inside of these parentheses, inside the function, that negative sign is going to cause a horizontal reflection, a reflection over the y-axis. Okay, so those are the two transformations that we need to apply. And visually, we're going to be applying those to the parent function. What's the parent function? I've got so many different things that I've circled that to point out the parent function, I'm afraid it's going to get lost. So let me erase a couple things. The parent function is really y equals b to the x, which in our case is y equals 3 to the x. So now you can really see that there's this additional negative to the left of the function, making it a negative 3, and there's a modification inside the function impacting the exponent, changing the exponent from an x to a negative x. So what does this parent function actually look like? Well, the 3 is positive, so I know that it's going to be this curve that's above the x-axis, and since it's larger than 1, it's going to start low in the second quadrant and curve up into the upper portions of the first quadrant. So it's going to cruise along and then curve up really fast like this. You might even say that the y values are growing exponentially. Okay, they start curving up very fast, and it crosses the y-axis at a y value of 1. And that's our parent function. Excuse me. Then we have to make our two modifications. We have to flip this thing horizontally, and we have to flip it vertically. The order in which we do those doesn't matter. So the first thing I'm going to do is the vertical flip, or the vertical reflection, and that's going to take all of our previous y values and negate them. So I've taken this point, which has a y value of positive 1. I've prepared to make it a y value of negative 1 right here. And if you wanted to think of this point as being approximately a y value of positive 2, then you could translate that down to a point or flip it over the x-axis so that it has a y value of negative 2. And that gives you a pretty good idea of where your curve needs to be after a vertical reflection. The next thing we'll do, am I going to run out of colors? I'm going to need another color. Let's maybe, how about orange? We'll see if that's distinct enough. Or this sort of fuchsia color. The next thing we're going to do is our horizontal reflection. So I'm going to take this equation and modify it even further. Let's write it as y equals negative 3 to the negative x. That negative going up in there causes that horizontal reflection, which means that anything that was to the right of the y-axis, like this point, is now going to be to the left of the y-axis. And anything that was to the left of the y-axis is now going to be to the right of the y-axis. I've tried to take those 2 points and only shift them horizontally, reflecting them or folding them over the y-axis. And then we'll draw our curve one last time, and whatever remains in purple is going to be our final answer. Or I think I called it fuchsia. See, it still needs to be passing through this point of negative 1, because when you take that point that was on the y-axis and flip it, it stays right where it was. So make sure your curve still passes through 0, negative 1. All right, that maybe not my best work. But that last curve that I drew is going to be our final answer. It's in the third and fourth quadrant. It's rising up into the fourth. It's diving down into the third. And let's look and see if we have multiple choice options. We do. And this looks like the one. I'm just double checking. Yes, it crosses my y-axis at negative 1. I think we're in good shape. So that process of taking your given equation and thinking of it as some sort of parent function, and then going through one modification at a time in order to determine what your final graph should look like, I find to be a very good technique. When I present this in an algebra class and we're working with parabolas, I do the exact same process. It works there, it works here. Another really great example of the fact that even as the functions become more complex, the process remains the same. Don't let the complexity of the function throw you. Again, it could be tangent, it could be cosecant. I don't care what it is. All those transformations, they frame up exactly the same. All right, number 5, starting with the graph of y equals e to the x. You should know pretty much what that looks like. Whether you want to go into an online grapher, or if you own a graphing calculator, or you want to look it up in the book, I'm sure that the ebook has a depiction of the graph of y equals e to the x. It's an exponential function where your base, e, which is a number that's larger than 2, in fact, is going to cross the y-axis at 1. It's going to be curving, rising to the right up into the first quadrant, skimming along the top of the x-axis as it goes off to the left. So the parent function, instead of saying it, why don't I just draw it, is going to look very much like this. It's y equals e to the x. I could tell you that that's y equals 2 to the x also. It's going to look a lot like that. Y equals 10 to the x is going to look a little bit different because it's going to still be curving along here and passing through 1, 1, but it's going to rise much faster if it were 10 to the x. All right, so what equation is going to represent this parent function shifted 7 units downward? That's a, let's just draw it generally here. If y equals f of x is our parent function, then if we were to implement all of the possible transformations we could write this as y equals a times f of, I'll go all the way with this, b times x minus h close plus k. If your a value is greater than 1, it's going to cause a vertical stretch. If your a value is between 0 and 1, it's going to cause a vertical shrink or a vertical compression. If your b value is greater than 1, it's going to cause a horizontal compression. It's a little bit backwards from what you might expect. It's counterintuitive. If your b value is between 0 and 1, it's going to cause a horizontal stretch. You have to be careful in here. If this says x minus 2, then you're looking at a horizontal shift. Again, if this said x minus 2, that would be a horizontal shift to the right 2 units. It would look like x minus 2, but it's going to shift it to the right 2 units. And if you've got a positive value added out here, a positive value would slide your graph up, negative value slides it down. I'm not sure if I said this because I'm really just doing all of this off the top of my head. I haven't even looked through this homework assignment more than once. And so let me just say one more time. If your a value is negative, if the multiplier outside your function is negative, and we saw this in the previous problem, it's going to cause a vertical reflection. Anything above the x-axis goes below, anything below gets reflected above. If your b value is negative, it's going to cause a reflection over the y-axis. Anything that was to the right of the y-axis flips over and appears to the left, and vice versa. These are all of the possible transformations that could occur to the graph of a function. Do they need to be applied in a particular order? I would work from the inside out. If you were being very strict about the application of the rules of these transformations, you would want to move horizontally. Is that true? Do you want to move horizontally first? No. You want to do some horizontal stretching first, then do some horizontal shifting, then you could stretch or shrink vertically, and then finally you could shift, slide your graph up or down vertically. So please apply your transformations in this order. It's more likely going to take you to a correct response. And now that you have this and the order in which they should be applied, and if you took some notes on what I was saying about if your a value is greater than 1, if your a value is between 0 and 1, if your a value is negative, if you've written all those down or if you already know them, then answering these questions at the left should be pretty easy. This is your shifting 4 units, and it's going to the right, which is a horizontal shift, which means we're looking at an h value. And if it's 4 units to the right, is this going to say x plus 4 or x minus 4? Don't forget, if it's inside the parentheses, it's counterintuitive. So if it says 4 units to the right, which is in the positive direction, it actually needs to say x minus 4. How does that apply to our natural exponential equation here? This would become, I don't have to write it up there. I could write it in the box where the final answer is supposed to go for this one. You would end up with y equals e to the x minus 4. That minus 4 subtracting positive 4 is going to slide your graph to the right. Reflecting about the x-axis, I already addressed that. Shifting 7 units downward, that's your k value. Just make sure, does it need to be positive 7 or negative 7? Reflecting over the y-axis in part D, we talked about that. Make sure, is it the a value, is it the b value, which one of those needs to become negative? Reflecting about the x and then about the y-axis. As it turns out, if the only modifications that you're applying are those 2 reflections, the order in which you do them doesn't matter. And This is an example of where we reflected over the x-axis and the y-axis. And if you did those in the other order from the way that we did them, you'll find you would get the same answer. And that puts us into question 6, where we have to find the domain of these functions. I don't know exactly how I would classify these particular questions. It's a real mixture. We've got some exponential expressions inside of these kind of gnarly looking equations or functions. And the question of domain still boils down to a couple of very basic traps, so to speak, that you want to watch out for. Anytime you're talking about a function, or originally, like in an algebra class when we started talking about functions, the things that you wanted to avoid were division by 0, square rooting a negative number. As you get further along in your study of math, you find that you're working with logarithms, and there are domain restrictions for logarithms. You can't take the log or the natural log, regardless of what the base is, of a number that's it has to be non-negative. Can't be a negative number, can't be 0. It has to be positive. Okay? In this case, we have a fraction in part A, and we want to make sure that we don't divide by 0, so we want to make sure that 1 minus e to the power of 49 minus x squared does not equal 0. How do we prevent that from happening? You should solve this equation that I've just written. 1 minus e to the power of 49 minus x squared, you should solve this. Not only that, and this may be bad news for you, you should know how to solve this already. I'm going to add e to the 49 minus x squared to both sides. That gives me 1 is not allowed to equal e to the 49 minus x squared. If they were equal to each other, then I'd have 1 minus 1, which would be 0, but we don't want it to equal 0. Okay, now I've got my variable, the x, which is being squared. It's in the exponent position. I don't like that. How do I bring it down onto the ground, as I like to say? How do I get it out of that exponent position? I'm going to take the natural log of both sides. That's just a little note about what I'm doing to both sides of my equation. What is the natural log of 1? Remember that the natural log of 1 is the same thing as saying log base e of 1. This expression is actually asking me a question. It's asking me e to what power equals 1? The base to what power equals 1? And the answer is anything to the power of what equals 1? Anything to the power of 0 equals 1. So that question mark is a 0, which means log base e of 1 is 0, which means the natural log of 1 is 0, which means that the left-hand side of our equation just became 0, because the natural log of 1 is 0. And what's the natural log of the right-hand side of the equation? That's a property of inverse functions, and natural log and the exponential, the natural log and the e, so to speak, cancel each other out, leaving us just with 49 minus x squared. We still need to solve for x. We still need to get x all alone on one side of the equation, so I'm now going to add x squared to both sides of the equation, which makes it appear on the right-hand side of the equation, which means that x squared is not allowed to equal 49. And then I'm going to take the square root of both sides of my equation, and I end up with x, not x squared. I just took the square root of both sides. That goes away. And what's the square root of 49? Yes, I'm really asking, what's the square root of 49? hopefully in your head, in your mind, not out loud, very begrudgingly, you're saying 7. Don't forget that the square root property says that the square root of 49 is also negative 7. So you should consider both positive and negative 7. If I took positive 7, so we did it. We solved for x. I'm not putting a box around this. I'm just circling it for a moment in order to draw this arrow, if my pen will work. If I take positive 7 and I plug it in for x, set positive 7 squared is 49. 49 minus 49 is 0. E to the 0, anything to the 0 is equal to 1, and then I'd have 1 minus 1, which is 0. Division by 0, not good, to be avoided. So we will not include positive 7 in our domain because it would cause division by 0. Now what happens if we use an x value of negative 7? Does that really still cause division by 0? It sure does, because negative 7 squared is positive 49. 49 minus 49 is still 0. E to the 0 is still equal to 1. 1 minus 1 is still equal to 0. Not good. Division by 0. So we will not be including negative 7 in our domain either. So if we're leaving those out, how do we answer the domain question? We need all real numbers except for those two. So remember, when you answer a domain question, you want to be answering with the list of x values that you are allowed to use, which in this case is, using interval notation, all of the x values that go from negative infinity up to negative 7, or, so we will unite that interval with the interval that starts at negative 7 but does not include negative 7. That's why we're using a parenthesis. Going up to positive 7, excluding it, united with, that's the union symbol. I'm uniting that interval with the interval that starts at 7 and goes all the way up to positive infinity. So that's the entire number line, but we have left out negative 7 and positive 7 by using parentheses at the negative 7 and positive 7. Part B also has a fraction, which means we also want to avoid division by 0, which means e to the cosine of x, we don't want it to equal 0. We talked in the previous video about the domain of some trig functions, and I think we actually addressed the domain of cosine specifically. And were there any restrictions on x values that were allowed to plug into the cosine function? And the answer was no. The cosine graph is a wave, sort of a curve, that goes all the way to the left and all the way to the right. And so the short answer is no restrictions. Negative infinity to positive infinity. Plug anything you want into the cosine function. But what about values that come out of the cosine function? What's the range of the cosine function? Well, it goes from negative 1 to positive 1, including negative and positive 1. If I take any of those range values for the cosine function, and I make them an exponent on e to the negative 1, e to the negative 0.257, e to the 0, e to the positive 0.3986, right, whatever, and what about e to the positive 1? Consider e being raised to any number from negative 1 to positive 1, all the decimals, all of them. Is there a possibility that I'm going to end up with a denominator of 0? No. You can't take a positive value like e and raise it to a power and get 0. But you knew that already. It doesn't matter. Oh, it's a highlighter. It's not writing very well. It doesn't matter what number, positive a half, positive a quarter, positive 10, positive 4, and so on. Doesn't matter what positive number you take and raise to the power, right? Those exponents could be anything. the resulting y value is never going to be 0. That's why all of these curves reside above the x-axis, because every point on every one of those curves has a y value greater than 0. Told you you knew already. So e to the power of is never going to involve or never going to result in a value of 0. So while it was good that we looked to make sure that we weren't going to accidentally cause division by 0 by plugging in an x value, turns out we're safe. Here a graphing calculator is recommended. It's nice because you can type it in on the screen and see it all play out. You could definitely do this with a scientific calculator. But if you happen to have a grapher, you could use that. A bacteria culture starts with 700 bacteria. It's doubling in size every half hour. How do you double something? Multiply it by 2. So after a half hour, I would have to take 700 and multiply it by 2. Well, what about after an hour? After an hour, that's 2 half hours. So I would have to take 700 and double it, and then double it again. So I'd have to multiply by 2 and then by 2. How many half hours are there in 3 hours? The answer is definitely 6. So I would have to take 700 and multiply it by 2 6 times. So in this case, I would have to take 700 and multiply it by 2 to the power of 6. How do I change a 3 into a 6? You're thinking double it, but it's close. How many half hours are there in 3 hours? 6. How do you use a 3 and a 1/2 to get a 6? Division. So the number of hours that went by, whether that's represented by a lowercase n or maybe a lowercase t as measured in hours, divided by 1/2, gave us the exponent that we needed to use. In this case, an exponent of 6. I'll leave you to use your calculator to do that arithmetic. I would type it in sort of in reverse order. 2 to the power of 6, get an answer, times 700 equals, there you go. How many bacteria are there after t hours? Darn it, I already gave you the answer. You could write that expression like this, or remember that dividing by a fraction, as we're doing here, division by a fraction is the same thing as multiplying by the reciprocal, so I would probably show off a little and clean it up and write it as 700 times 2 to the power of 2t. All right, that would generate the number of bacteria present after t hours. How many bacteria are there after 40 minutes? That's a little trickier. If t is measured in hours, then to answer this question, you need to convert 40 minutes into hours. This is a real throwback. 40 minutes. This is a unit conversion problem all of a sudden. So this is taking us back to maybe late grade school, late middle school. I'm going to multiply this by, I need to convert it into hours, so I need some number of hours to remain. Some number of hours to remain, and I want to cancel out minutes. Yep, I can see that the minutes would cancel there. That would be good, leaving me just with hours. And I'm going to use 1 hour in the numerator and 60 minutes in the denominator. And why am I allowed to take 40 minutes and multiply it by 1 hour over 60 minutes? Because 1 hour and 60 minutes are the same, which means I've just multiplied by a fraction where my numerator and denominator are the same, which means that this fraction is equal to 1. The units are changing, but I'm still multiplying by 1. And what happens when you multiply by 1? Nothing. it's going to change what it looks like in this case, but the value ultimately is going to be the same. So minutes cancel, the multiples of 10 cancel, 4 over 6, 4/6 hours. You could reduce that and make it into 2/3 hours. That's not much of a 2. It's a good thing I'm saying it out loud also. 2, there we go, that's more like a 2. 2/3 hours. This is the t value that you want to plug into the function that we just designed in part B. I'll leave you to process that using your graphing or scientific calculator. That's just arithmetic. Graph the population function. If you have a grapher, you can do it. If you'll look up at the function in part B with me, this is an exponential function. You have a base, which is a number, in this case 2. It's being raised to an exponent that contains the variable, t in this case. So you have here an exponential function. You know what 2 to the x looks like when you graph it. You know that if you have this additional multiple of 2 in your exponent position, that's going to cause is it going to be a horizontal stretch or shrink? Because it's inside the function, it's counterintuitive, it's going to cause a horizontal shrink, not a stretch. So we're compressing the graph from the side, so that graph that normally curved up into the first quadrant is now stretched out to the right. But then look at this a value in front of it, 700. We're taking all of our old y values and multiplying them by 700. So this thing is going up into the first quadrant and it's climbing fast. All right, so that can be mitigated by changing the scale on your actual graph, but boy, that one to the right there looks pretty good. That thing's going up awfully fast. Do we have any other options that look like that? Ooh, this other one in the bottom right is a contender because it's also rising. As time is going forward, the population of bacteria is increasing. We should probably consider the starting population of bacteria. Here, I can't even zoom in far enough. I have to keep my fingers on the screen in order to stay zoomed in or it snaps out. Boy, if this is 10,000, 1, 2, 3, 4, I'm looking at like 5,000 here. It's counting by 2,000. It's a pretty small number, less than 1,000. Oh, I'm looking at the original question. A bacteria culture starts with 700 bacteria. That's less than 1,000. I think that's probably a good starting value. Let's look just quickly at this other one. Oh yeah, this is starting, that's more like 10,700. I don't think that's it. I think the graph in the top right corner, I think that's probably our right answer. All right, so applied problems, word problems. Estimate the time for the population to reach 40,000. This equation or this function that we designed up here in part B, oh, I didn't mean to erase the whole thing. I just wanted to erase the green stuff. I wish I could do color specific erasing. Wouldn't it be nice to have a filter on my pen for erasing? The y value in that function is the population. Sometimes that would be represented as capital P of t, population at time t. The left-hand side of this equation needs to be, we need to replace the y value with 40,000. And then you need to solve the equation for t. You're going to use a similar trick in order to get this t value down onto the ground. Use a similar trick as we did in the previous problem where we had to take the natural log of both sides. Okay? In this case, you are also going to take the natural log of both sides, and that'll allow you to bring the exponent down onto the ground. Little tricky though, because this is not e, which means the natural log and that 2 are not going to cancel out. I'm starting to think maybe I should do this one with you. let's get it started anyway. 40,000 equals 700 times 2 to the 2t. Divide both sides by 700, and you end up with 40,000 over 700 equals 2 to the 2t. Reduce this, divide, knock out a couple of zeros there, and then, I'm running out of real estate. Let me move over here. I'm going to take the natural log of both sides, which means on the left-hand side, I'll be taking the natural log, ln, of 400 over 7. And on the right-hand side, the natural log of 2 to the 2t. How does that help me get the variable out of my exponent position? There's a property of logarithms that you should be aware of already that says that I can take the exponent and bring it out front of my natural log. That is the power rule for logarithms. You should probably refresh your memory on the rules for logarithms and natural logs. There's a power rule, a product rule, and a quotient rule. Okay, make a note in your notebook to look those up. It'll be a real simple little illustration that you can find. Look it up online, jot that into your notes. This is a reverse power rule, I would say, since we're taking the exponent and putting it out front. So I have whatever this number turns out to be. It's going to be a gnarly decimal. I wouldn't actually write it down. It's something that you're just going to leave in your calculator. We've got 2t times the natural log of 2, and you now need to divide both sides of your equation by 2 and both sides of your equation by the natural log of 2. So when you type that into your calculator, I would first type in 400 divided by 7. If you're on a scientific calculator, and it depends on which calculator you're on, I use the TI-30XA, which does not allow me to type in an entire line of text. So on my calculator, I'd have to type in 400 over 7 and hit enter, and then I would take the natural log of whatever answer that was. As soon as I hit ln, it would give me a new decimal on the screen, and then I would hit divided by 2, and then, this is really terrible on my calculator, I would have to then hit divided by 2, so I would type divided by, and then I would hit the number 2, and then I would hit the ln button, and then make sure to hit equals. So again, if you're using the TI-30XA, or a scientific calculator that only allows for single line input, this is probably the order that you're going to have to type in your last set of keystrokes. All right, I don't have that calculator here with me, so I can't generate a final answer for you, but estimate the time of population, round your answer to 1 decimal place. All right, so when you're typing in an answer like this, if you're using WebAssign, make sure you follow those last little bit of instructions and round to 1 decimal place. I will try to remember to put a numerical answer for this question in the notes on the video. All right, we've got questions 8 and 9 and 10 and 11 and 12. All right, so good progress. This is good review. This is a half-life problem. Sample has a mass of, let's see, half-life is 5 days. What a half-life means, don't forget, is that if you're starting out with 208 milligrams of bismuth, after 5 days, half of it would have deteriorated or evaporated or whatever the scenario is. So after 5 days, you would only have 104 milligrams. And then after another 5 days, you would have half of that. And after another 5 days, half of that. So this is a similar situation to what we ran into up here, where my exponent, it became 2 to the power of not just t, but it was t divided by 1/2. And we took that and turned it into a 2t, because division by a fraction is the same thing as multiplying by the reciprocal. So we're going to have to do something similar here. I'm actually going to answer you can answer part A first. How many 5-day periods are there in 15 days? In other words, how many times does 5 go into 15? 3. So how many times will we need to half the original amount of bismuth? We will have to half that number, or multiply it by 0.5, or multiply it by 1/2, 3 times. So you can take the 208 and multiply it by 1/2 to the 3rd power, however you want to do that. Find the amount remaining after t days. We're definitely using a starting amount of 208 milligrams. We're definitely going to be multiplying by 1/2, but to what power? Is the answer t? Well, let's look at the number 5 for a time period. After 5 days, you should only have half of your original amount remaining. If I take the number 5 and I put it in there as an exponent, I'm going to be taking the number 208 and multiplying it by 1/2, and then times 1/2, and then times 1/2. I'm going to end up with a 32nd of my original amount instead of 1/2 of my original amount. So we can't just use an exponent of t. When time is 5, I need that exponent to be a 1. After 5 days, I want to be halving my quantity once. So I think it's safe to say that this t value is going to need to be divided by 5. Let's see if that works with part A. If we take a time value of 15 days, plug it in for t, 15 divided by 5, that's exactly what we just did. That's how we got our exponent of 3. Perfect. Okay, so I think we've got a good equation there. Estimate the time, or the amount remaining after 2 weeks. Can't put in 2 for t. T is measured in days, so convert 2 weeks to a number of days, plug it in, use your calculator, round your answer to 1 decimal place. Use a graph to estimate the time required for the mass to be reduced to 1 milligram. You can do that. You can do it using a grapher and use intersect mode. I'm not going to demonstrate that here on a TI graphing calculator. You can certainly do it. If you graphed our original function here as your first equation, and if you graph y equals 1 as your second equation, and you did it in Desmos, for example, you could just drag your cursor to the point of intersection and click, and it will show you the x and y coordinates of that point of intersection. The y coordinate will be 1, and the x coordinate will actually be a t value, measured in days, and then you'll have to round to 1 decimal place. You can also solve this algebraically, just using arithmetic, and you would use the exact same technique that we did in the previous problem up here, using the natural log in the same way, and the reverse power rule in order to get your exponent down on the ground, as I like to say, and you got some kind of gnarly looking division. Look at my little orange notations that are down here about the order in which you have to type that into your calculator. It's a little bit of a pain, but you can definitely do it algebraically. I would do it algebraically. Use the following graph to estimate the half-life of the viral load of patient 303 during the first month of treatment. The horizontal axis here is measured in days. RNA copies per milliliter is the vertical axis. We're estimating the half-life of the viral load. RNA copies per milliliter must be an indicator or a measurement of viral load. All right, I'm not a virologist, so I don't know, but that's my guess. And the question is to estimate the half-life. Half-life is the amount of time after which half of an amount has evaporated or deteriorated. So let's pick a couple of points and see how long it takes half of our viral load to dissipate. This point right here, looks like it has an x-coordinate of, I don't know, 4 maybe? And it has a y value of, I don't know, 55. What's half of 55? 27 and change. So this is 30, so maybe 27 and a half is here. And we could drop that down to the x-axis, and that looks like it's about 6, right? So that, it looks like maybe 2 days is how long it takes for half of a previous quantity to dissipate. So we could do that. We could use, we could try to find 2 of these blue dots that vertically are half of one another, right? So this one was like 55, and this one's 20, but 20 is not half of 55. So those would not be 2 good points to choose. Let's try a different pair of points. Oh boy, where did we go? Here we are. What about this point and this point? Let's look at their y values. This one's like 19. Could this one be 9.5? Yeah, could be. Those look like they have y values that are about half of one another. And what about the corresponding x coordinates or t coordinates? Could this be, do you think that's 8? And this looks like it's, is that 11? That's a spread of about 3 days. That's the tough part about graphing. It's why I much preferred to solve the previous question, part D right here, why I would much rather do it algebraically instead of graphically, because graphically it's just not accurate enough for me. So I'm afraid on this one you might have to try an answer of 2 and see if it's correct, and then if it's not, then try 3. But that's the technique that you would want to use there. Find the domain of the function. Again, fractions don't want to cause division by 0. Will this ever equal -4? If the answer is no, then you don't have any restrictions. Could this possibly equal 1, so that you have 1 minus 1? Well, is it possible to take a number like e and raise it to a power? Can I take a number and raise it to a power and end up with 0? Or sorry, raise it to a power and end up with 1? Can I take a number and raise it to a power and end up with 1? Sure can. Right, so what exponent would we want to avoid so that e to the x doesn't equal 1? We want to make sure that e to the x does not equal 1. I'll leave it to you to remember what exponent we would want to avoid in that case. This is a throwback question. Find the slope of the line passing through those 2 points. Remember that slope is equal to y2 minus y1 over x2 minus x1. That is rise over run, right? Difference in y values divided by the difference in x values. Why would I be asked this question in a calculus class? Why would I be concerned with rate of change or slope? Hang in there, you'll see. We'll come back to it for sure, big time. That's a big component of the course. Find an equation of the line passing through the given points. Why would I want to do that? I promise you, this is a task which we're going to see again later, except instead of finding the slope through these 2 points, we're going to be finding slope a different way, and we're going to be using infinity, and we're going to be cutting things into infinitely many pieces that have a width of almost 0, and we're going to get 2 things that are almost touching, but we're going to get them infinitely close together. We're going to go ballistic with this stuff. But we still have to remember our algebra skills. So again, you're going to need to first find your m value. So figure out what your slope is equal to, and that's your slope. And then you'll use a point, maybe this point or this point, and you'll need to use point slope form, which is y minus y1 equals m times the quantity x minus x1. Your slope is going to be here, and maybe this will be x1 comma y1. You'll plug those 2 values in to here, and you'll write an equation for the line. And then you'll sketch the line. So you'll have to choose from those graphs. And then if you're one of my students, you're going to be done with your homework. And if you're somebody else's student, then it's probably time for you to go start your own homework. Thanks so much for hanging with me through that review. I look forward to seeing you next time.